Hello. In the last lecture we discussed about comparators and subtractor. Now we move on and we see the next element or component in computers, which is ALU. This is the pretty important one. So let's see how it is working. So first of all, what is an ALU? An ALU is a digital device or a logic device which can do certain number of operations on two numbers, right? Two n-bit numbers. So here in the schematic given you have the symbol for ALU, and remember this is the symbol for any. This can be used as a symbol for any device or any component which takes in two inputs and gives one output. Okay, this is a generic symbol, depends on what is written inside, the meaning changes. So here we are using this symbol for an ALU. Okay, it has two inputs, two n-bit inputs, A and B. It has one n-bit output Y, and it can do certain operations, right? So these operations, which operation is being performed on the two inputs is decided by this one, function, right? ALU function. So this is an m bit. This m depends on depends on the designer and how many operations he or she is planning to implement using the particular ALU, right? Okay, now let's consider an n bit ALU which can do 7 functions, right? So this is basically the truth table for it. So F220 will be 0002 111. So there are basically 8 combinations, and the functions that we are trying to implement here is A and B, A or B, A plus B. This is arithmetic operation, A plus B. This is nothing. For 011 there is no operation. Then A and B bar, A or B bar, A minus B, and set if less than. Set if less than is if A is less than B, then the output should be 1, right? So these are the 7 operations that we are planning to implement, and the selection of these 7 operations is just to illustrate how an ALU is designed. There is nothing more than that, right? Moving on. So first of all, if we look here, A is in this whole operation, A doesn't have to be complemented, right? A is always used as it is. So we are taking the input A directly. But B, for the first 3 operations, right, or first 3 operations, B is taken as it is. But for the other 3 operations, right, these 3 operations, B has to be inverted. So that is why here we are using a multiplexer and an inverter to take either B or B bar. So here, if this input is 0, we will get B here. If this input is 1, we will get B bar here. So this is control using F2. Why are we using F2 here? That is actually part of the design. Here, see, for functions or operations where we want B, the F2, this F2 to 0 is F2, F1, F0. Pretty standard stuff. So here F2 is 0, B is taken as B itself, and here if F2 is 1, B is taken as B bar. Here we are using A minus B, means how are we implementing A minus B? It is A plus 2's complement of B, that is A plus 1's complement of B plus 1. So here also we need to take the complement or inversion of B. So that is the logic. If F2 is 0, then we use B itself. If F2 is 1, we use B bar. Okay. Then here for the addition, so what does this one do? This one does what? A plus B or A minus B, right? A plus B or A minus B. What does this one do? This one does A or B and also A or B bar. What about this one? A and B, also A and B bar, right? Here we are taking F2 here directly as the C input, so that A comes here, B bar comes here, that is 1's complement of B comes here, and 1 comes here. So this will be 2's complement, like that, right? So now we have connecting these things to another multiplexer from which we are taking the output, and this is a 0 extent, that is 0 extent is, or just sign extent, sorry, this is not 0 extent, this is a sign extent. It is simply a device which extends whatever input is coming there into n bits. For example, if a one single 0 comes here, it will take that single 0 and make it into n zeros, and if a single 1 comes here, it will take that single 1 and make it into n ones. So this is a extension, 0 extension or sign extension, depends on the context actually. Basically an extension device, right? So here we are putting F2, F1, F0, right? F1, F0 is the select inputs to this multiplexer. So what happens? Let's consider we are using F2 equal to 0. So 0, 0, 0 means 0, 0. Here it will be 0, 0, and this one is selected, which is A and B, right? That is what we want, A and B. If we select, say, 1, 0, 0, let's see what happens. 1, 0, 0 means here B bar will come to all these three, and here it will be 0, 0. So we will get A and B bar here will come to the output. And let's say if we want A minus B, what happens? This becomes 1, right? F2 becomes 1. So we will get B bar here again, and here 1 will come. So output will be, here it will be A minus B, here it will be A or B bar, here it will be A and B bar, and here it will be depending on whether A is less than or greater than B, it will be either an n bit 1 or an n bit 0. So what is the value here? We have chosen this one, right? 1, 0. 1, 0 means 2. So this input will come here, and we will get A minus B as the output. Like that you can check for the other input output combinations also. So if you are interested, you can try different functionalities, and higher number of functionalities. If you can manage it, it will be a good exercise to do. So this is the basic implementation and working of this is a hypothetical ALU. This may not be the way an actual functioning ALU is implemented, but this will give you a sense of how you can actually design a device which can do multiple functions based on certain selection criteria or inputs. Okay, now moving on to the next topic, we will consider the topic of shifters and rotators. Okay, now first of all, let's see the schematic or symbol, then we will see how it is, what the actual logic is, and then how it is. We will see an example implementation of the device. Okay, first of all, shifting can be of two types: logical shift and arithmetic shift. We'll see the difference in a minute. So this is the symbol. 2 arrows indicate logical shift and 3 arrows indicate arithmetic shift, right? So when we are considering the symbol, there will be a box, and there will be arrows indicating firstly the type of shift and the direction of the shift. That is, 2 arrows to the left is a logical left shift. 3 arrows to the left is a arithmetic left shift. Similarly, 2 arrows to the right is a logical right shift, and 3 arrows to the right is an arithmetic right shift. So input, there are 2 inputs. First of all, the actual number to be shifted to right or left, arithmetic or logic, doesn't matter. The input to be shifted, and then the shift amount. Shift amount is the number of bits to be shifted or number of places to be shifted right or left, right? So if the let's say here given in the example the input is of 4 bits, right? A3 to 0, 4-bit input. 4-bit input means the shift, there should be a shift, there can be a shift from 0 to 3, right? So here we are using 2. Here we are using 2 bits to denote that 4 combinations. That is, if the input is of 2 to the power of n, then the shift amount will be n bits. If the input is 2 to the power of n bits, input will be shift amount will be n bits. This applies for all. The next thing, this is shifters, logical shifters, arithmetic shifters, left shifters, right shifters. Then this is rotate, rotate left and rotate right. So shifting we'll see with an example. Okay, 11001, left shift, logical shift right by 2. Here is what is happening. This whole number is just pushed to the right by 2 bits. So this 110 is coming here, right? This 110 is coming here. These two numbers, these 2 bits are lost, they are removed because it's a shift, right? But if you consider a rotate, this is 1101 rotate right by 2, means this whole thing is rotated. Here the last 2 bits are lost, but here it is not like that. By one rotate, this 1 will come here. For the next rotate, the 0 will come here. So it will be like the whole thing is, first of all, these 3 will be shifted here and this will be shifted one by one here. That is rotate. So basically the main difference between shift and rotate is that in shifting we are actually losing bits, but in rotate we are not losing bits, we are just rearranging them, let's say, right? It's like consider the way in which numbers are posted on the periphery of a circle, okay, and it is rotated, so nothing is lost. But for shifting you can consider it like it is a straight line, and the more you move, numbers you are losing. So this is left, logical shift to the right. Then what is logical shift to the left? This is 11001 logical shift left by 2. So this will move to the left, means these 3 will be here, these 2 are lost, and here zeros. Again here in rotate, no number is lost, right? No bit is lost, so there need not be any substitution. But in shifting, here we are shifting to the right by 2, so we lost 2 numbers, 2 bits, we replace it with zeros. Here we shifted left by 2, so we lost 2 bits, we substitute it with zeros. This is logical shift and rotate. Here this is arithmetic shift. Arithmetic shift right means again by 2, means these 3 will become the last 3. But if you compare logical shift and arithmetic shift, what is happening here? It is 2 ones, right? Here it is 2 ones. This 110 is coming from here, but these are 2 ones for the arithmetic shift, and these are 2 zeros for the logical shift, right? So what is the difference? Actually this is not 1, this is the MSB. This is the MSB being extended. If it was a 0 here, it would have been 0 0. Since it is 1 here, these are ones. So the the only difference between arithmetic shift and logical shift is that when you are shifting right, in logical shift, the new empty slots are being filled by zeros, and in arithmetic shift, the empty slots are being filled by the MSB, not ones, not zeros, MSB, whatever is in the MSB, it will be used to fill the empty slots. Arithmetic shift left, it is the same as logical shift left. The empty slots are being filled with zeros. This is rotate left by 2. The same logic as here, but the rotation will be in the other opposite direction. One thing to remember is that please don't confuse this with shift registers that you learned in sequential circuits. Those are circuits, sequential circuits in which you can continuously keep on shifting and rotating the bits. This is not like that. The way this works is once you get an input, okay, it is shifted or rotated by how many numbers you want, okay, that is done, then that output is taken, new input comes, like that. Yes, you can implement this logic using shift registers, but essentially they are not the same. There is a difference. Okay. Now this is an example of a 4-bit arithmetic shift right. Okay, arithmetic shift right. It is implemented using multiplexers. 4-bit numbers the input, so there will be 4:1 multiplexers. So let's see, this is the shift amount input, right? It is given here. So let's consider the MSB. So for an arithmetic right shift, MSB is always MSB. No matter how many shift is being happened, it is always MSB. So all the inputs are connected to A3. For the second bit, that is a bit next to the MSB, if there is no shift, the value will be A2. But if there is even one shift, for one shift it will be A3, for two shift it will be A3, for three shifts it will be A3. So that 0 input is connected to A2 and the remaining are connected to A3. Here the bit next to that, by default, that is if there is no shift, it will be A1, for one shift it will be A2, and for the remaining 2 and 3 shifts it will be A3. And here for the LSB, it will be initially it will be A0, then for one shift it will be A1, for two shifts it will be A2, and for three shifts it will be A3, right? So this is the logic of implementing a arithmetic right shift. So like consider the case when if this was a 4-bit logical right shift instead of an arithmetic right shift. If it was a logical right shift, then what would have happened? Here these 3 inputs, right? These 3 inputs wouldn't be connected to A3. These would have been zeros, because obviously for no shift A3 should come, then for the next shift it should be 0, for 2 shifts it will be 0, right? Similarly here for 0 shift it will be connected to A2, for one shift it will be connected to A1, then for the next second and third shift it will be connected to zeros, like that for these, remember. So try to implement the other shift and rotate logics using this multiplexers. Okay, so I'm stopping the lecture here. We'll continue with multiplication and division in the next lecture. Thank you.